Okay, everyone. In this video, we're going to cover experiment 19, which is electrochemical cells and thermodynamics. For the next two labs, we're going to be looking at electrochemical cells. And there are two main classes we know from class. The first is voltaic cells, and the second is electrolytic cells. So in experiment 19, we're going to look at voltaic cells. And then in experiment 20, we're going to look at an electrolytic cell. So to kind of refresh your memory of electrochemical cells, we use the example in a lot of our lecture videos of batteries. And here I show two pictures. So we have the battery. This is the battery that would go inside of an iPhone. And then this guy over here, this is the battery that goes inside of a Tesla. So obviously it's much bigger. Now we know that there are two modes that our cell phone battery can be in. So when you turn on your cell phone for the first time and the battery has already been charged, and we need the battery to power our phone, we're using that battery as a voltaic cell. The cell is discharging by sending electrons from the anode to the cathode, and the cell potential has got to have a positive cell potential. Now, the reason why it has to be a positive cell potential is because when we have positive cell potentials, that gives us a negative value for delta G, and then we can get work out of our cell. So when you are driving down the road in your Tesla, that cell is working as a voltaic cell, and the E cell is going to be such that it's spontaneous and is going to have a positive cell potential, a negative value for delta G, and can do work. Now, when you're done driving your Tesla for the day and you come home and you park it, you have to charge the battery back up. So at that point, when you plug it in, you're plugging it into the wall and you're applying a negative bias across that cell. So basically what you're doing is you're pushing the cell to go in the opposite direction. This is in the electrolytic form. This is the electrolytic form of the cell, meaning you are going against the spontaneous direction of the cell, pushing electrons back and charging it up. So you're putting electrons back into what was the anode and taking electrons away from the cathode. So in essence, your cathode and anode flip, and you're driving electrons in the reverse direction. So we're going to look at the electrolytic cell form of this in the next experiment, where we have to put electrical energy in because the cell potential is a negative. Okay, so the cell that we're going to look at today is the Daniell cell, and you should remember this slide from lecture. In the Daniell cell, we have a zinc electrode that's in a solution of zinc 2+, that's at 1 molar. And we have a copper electrode that's in a solution of copper 2+ at 1 molar. And then we connect these things up with a salt bridge, which allows ions to flow across. And we hook them also up with a wire, which allows electrons to flow across. So the zinc in the Daniell cell is going to be the anode, and the copper is going to be the cathode. So at the zinc anode, as the cell reaction progresses, the zinc metal gets dissolved to being zinc 2+. It gives up 2 electrons which go around the external circuit and to the copper, and those electrons reduce copper, making the copper electrode grow in size because copper 2+ becomes copper metal. Now the role of the salt bridge is to make sure that we have charge neutrality. As electrons flow from the anode to the cathode, we can't have a buildup of electrons in any one particular place. So positive ions must also flow across in the same direction and in the same current or the same rate of flow as those electrons. And that's what the purpose of the salt bridge is. That maintains charge neutrality as electrons move around. And it does that by allowing the ions to flow. So how did I know that when I hooked this cell up that the copper was going to be the cathode and that the zinc was going to be the anode? And this is from the standard reduction potentials of those electrodes. So if you remember about standard reduction potentials from lecture, the standard reduction potential is a measure of how much something wants to be reduced. So we have all of these different processes here, and you'll notice that every single one of these processes has electrons as a reactant, meaning these are all going to be reductions. And we sort of rate them from something that's very negative to something that's very positive. So numbers that are more positive or higher in magnitude tend to be those tend to favor reduction, So as we go down this list, these are going to be the processes that would tend to want to be reduction reactions. So if we look at copper 2 plus 2 electrons goes to copper is at 0.34 volts. If we look at zinc 2 plus 2 electrons goes to zinc is minus 0.76 volts. So clearly the copper 2 plus 2 electrons is more positive, and will therefore, when we hook this thing up as a cell and allow it to go in the spontaneous direction, the copper is going to want the electrons because it has a higher positive standard reduction potential. Another way to think of this is when you're building a field, the electrons are always going to want to go to the more positive place, meaning there's a negative place and a positive place in a potential field, and the electrons are going to want to go toward the positive place in that field. So the fact that the copper has a higher standard reduction potential means that it's going to want the electrons more. So we have those standard reduction potentials from the table from the previous table, and I brought them over here. So we have zinc 2 plus 2 electrons goes to zinc, and copper 2 plus 2 electrons goes to copper. And the E naughts were minus 0.76 and plus 0.34. So now the question is how do we calculate the standard cell potential for this cell? Well, the first step is we have to write down the half reactions for each of those reactions. So if you look, zinc goes to zinc 2 plus. Zinc is being oxidized by 2 electrons to go to zinc 2 plus. And then we have copper 2 plus goes to copper. This is a reduction, and it's a reduction by 2 electrons. So if we pull the reactant in the product, we have zinc goes to zinc 2 plus, and copper 2 plus goes to copper. Then we balance the charge with electrons. So if there are 2 positive charges here, we have to have 2 negative charges along with it to maintain a overall zero charge, which is on the left. And the same thing goes for the cathode. So that's how we write the half reactions. Now, if we want to figure out the cell potential, we have 2 options. So option 1 is we can say, well, the copper 2 plus 2 electrons goes to copper. That's the same as this exact standard reduction potential, so we can throw that in here. We notice, though, that the zinc anode is flipped. So relative to the standard reduction potential, this is going in the other direction. So to account for that, we can take the standard reduction potential and multiply it by -1, essentially flip the sign in order to account for the fact that the reaction is flipped. And then we can add those up and get an E cell of plus 1.1 volts. So you can flip the sign of the standard reduction potential for the anode and get the overall cell potential. Now my preference is to forego all of this flipping and just take the values from the chart directly. So we have this equation where we know that the E of the cathode is always going to be minus the E of the anode. The reason why we have the minus sign here is because it accounts for the flip. So all you have to do is grab the numbers directly from the chart. So I didn't do anything to these numbers. I just took the plus 0.34 and the minus 0.76 exactly as they came from the chart. And then I just take the cathode and subtract away the anode, and I get the same exact value. So this is my preference for how to do it, because this is how electrochemists do it. But you can also do it this way. The only problem is you can't do it together, meaning you can't do both. So if you put the minus sign and you flip the chart, the sign of this, you're going to wind up with the wrong number. So you can't double up. You can only do one or the other. Now, I'm not going to be going through all of the equations that we have in the textbook for this, but I am going to show you this figure, because this figure is incredibly important. You should take a look at this figure, especially when you're doing lecture problems and doing lab problems, because this figure summarizes all of electrochemistry and all of thermodynamics in one nice figure. So what we're going to be doing today is our job is going to be to determine the electrochemical data. We're going to measure the cell potential of the Daniell cell. And we're going to do that at a few different temperatures. And then what we're going to do is we're going to take this data and we're going to calculate a variety of different things. We're going to use this data to figure out delta H and delta S data by converting the E cell to delta G. So we know that the relationship between delta G and E cell is that delta G is equal to minus NFE. So if we want to go between the electrochemical data and delta G, we can use minus NFE cell as the relationship. Then once we have delta G, we have a lot of options for calculating different things. So one of our jobs today is going to be to take those delta G's and we're going to plot them as a function of temperature, and we're going to use that plot to come up with delta H and delta S, and I'll show you how we're going to do that in a minute. The other thing we're going to do is we're going to use delta G to get K. Now it turns out that you have two options here. If you know delta G, if you know delta G naught, I should say, the standard Gibbs free energy change for the reaction, you can use the equation minus RT ln K to get the equilibrium constant. We can also use this equation E cell, which is just a derivation of these two equations, to get the ln K directly. So that's your choice of how you want to do it. But these are all the relevant equations and how we're going to use them. So now let's look at the temperature effect on the Gibbs free energy. So in lecture we had spoken about this. We had said that if we have delta H and we have delta S, and these are values that we look up in a table. So these should actually have little knots here because these are the standard enthalpy change and the standard entropy change. I forgot them, but anyway. So delta H naught and delta S naught are things that you can look up in a table. And we know that these things tend to not change very much as a function of temperature. So if that's true, we can calculate delta G at any temperature using delta H minus T delta S, where the temperature is not necessarily at 298 Kelvin. Another way of looking at this is if we vary the temperature and we have a way of measuring delta G, we can create a graph that looks something like this. We can say, well, delta G is like a y, the delta H is like a y-intercept, and then the temperature is like our x variable, and our delta S, our minus delta S, is like our slope. So in essence, we're converting this equation into a line function and creating a temperature-dependent plot. Now, this graph is the graph that you would generate for the Daniels cell if you were to change the temperature and measure the Gibbs free energy. So this is the perfect graph, meaning I calculated delta H and delta S from the textbook values of delta H and delta S for this reaction, and I plotted the data out. So you can see it makes a nice straight line, which I can draw a best fit straight line through the data points. And it's going to follow a linear equation. So you can see that our y is the Gibbs free energy, as we had here. Our x is the temperature, which we have here. So then what this means is that our slope of this line, if t is x, then our slope is going to be minus delta S. And this slope is going to have units of kilojoules per mole because of the fact that our delta G is reported in kilojoules per mole. So just keep that in mind when you're working with the slope for your graph that you're going to make in lab today, in virtual lab today. So now the other important data point along here is the y-intercept. So the b, which is the y-intercept in a line equation, corresponds to the delta H. So we can get the delta H directly from where this line crosses the 0. Now I've purposefully left this line a little bit away from the 0, but the crossing point of your data, where it literally crosses through that x-axis, is going to be the delta H. And then we can get another thing too. If we want to get delta G naught, we know that what distinguishes delta G from delta G naught is that delta G naught is under standard conditions. So if we construct our cell, our electrochemical cell, to have 1 molar zinc and 1 molar copper 2 plus, zinc 2 plus and copper 2 plus, we've accounted for the concentration component of it being a standard cell. So what we can do then is at 298 Kelvin, we can go in and look and see what is the delta G at 298 Kelvin. And whatever the delta G that we read off here, that delta G is going to be equal to delta G naught at 298 Kelvin. So these are the 3 things that we need to get from our graph today that we're going to make. Okay, so how are we going to get delta G? Well, we're going to get delta G by building an electrochemical cell and measuring the E cell. So let's see how we're going to build the cell. So the good thing about this lab is that we would actually set this demonstration up exactly as it is in this video. A few minor changes, but exactly as it is in this video. And I will highlight the changes to you. But you wouldn't actually do this experiment, you'd watch us do it anyway. So you're not really missing out on anything, and you're going to get a chance to see exactly what we do. So we're going to skip ahead just a little bit, and what we're going to have is we need the two electrodes. So you'll notice they have some copper here and some zinc here. And then you'll also notice that they have this sort of U-shaped tube. Let me just go back a second. This U-shaped tube is the salt bridge. So this is what's going to allow for ions to be transduced from the anode to the cathode. Okay, so that's the salt bridge, that part. Okay, so let's take a look and see how they assemble everything. So now in this particular video, there's something I just want to highlight here. They're using 0.5 molar and 0.5 molar of the zinc and the copper. We would use 1 molar in our setup. So you're going to notice that their voltage is going to be a little different from the standard voltage. And the reason for that is because they're using a different concentration. So you'd have to actually use the Nernst equation, which accounts for differences in concentration, to figure out what the voltage should be at those concentrations. And so what they did was they took their zinc and their copper and they put them into two beakers. Now what they have here is they have their two electrodes and they're hooking them up to a multimeter, which is going to measure the voltage. And you'll notice that if you look at this copper electrode, they didn't show it, but if you look down at the bottom of it, you can see that they cleaned it off a little bit with some sandpaper. And that's just, they did that for both electrodes. And that's just to get the sandpaper, that's just to get the electrode clean and have some fresh metal there. So you're going to notice that they're putting the voltmeter into volt measurement mode. So they're going to be able to measure direct current voltage. Now they've connected their salt bridge across to their two anode and cathode, to their anode and their cathode beakers. And then they're going to hook the cell up now by allowing the copper and zinc electrodes to go into their respective solutions. And you'll notice as soon as the electrodes are immersed, they get a value that's pretty close to 1.1 volts, which is what we would expect for the thermodynamic potential for this cell. So that's the setup, and this is exactly like the cell that we would have. The only difference between their cell and our cell is instead of using this type of salt bridge, we use a little bit different type of salt bridge that connects the two cells this way. So our two beakers would be connected by a salt bridge in the middle, but that has no significant effect on the way it's set up. And we would measure the cell potential exactly like this. We would use a multimeter to measure the cell potential just like they're using. So now in our experiment, we're going to vary the temperature of the cell from 0 degrees Celsius to 65 degrees Celsius and measure the potential. So the way that we're going to do that is we're going to take our beakers and we're going to put them into either ice cold water and allow the beaker and the liquid and the electrodes to come down in temperature to ice cold water temperature, or we're going to put them into a little heater that heats them up to about 65 degrees Celsius. And then we're going to take the cold one and measure its potential with a salt bridge, take the warm one, measure its potential with a salt bridge, and we're going to record those potentials. So if you look, this is what we did today in lab. So we set the cell up just that way. We had one at room temperature, or about 16.5 degrees Celsius. We had one that was cooled down to close to ice water temperature, which was at 1.9 degrees Celsius. And we had one that was heated up to 64.6 degrees Celsius. And then these were the cell potentials that we got. We got 1.1, 1.098, and 1.096. Now we've added in a few extra data points here for you to help you extend your line out. So basically, what we did was we can't create these data points in our lab, but we did it where you could theoretically get these data points, and then we included them for you to plot. Okay, so what you're going to do is you're going to use the graph paper on page 287 to create your plot. So the first thing you have to do is convert these temperatures to temperatures in Kelvin. And then the next thing you have to do is convert these delta G's, these E cells, into delta G's. The equation that we're going to use for that is delta G is equal to minus NF E cell. So where N is the number of electrons that are transferred, F is Faraday's constant, and E cell is the cell that's measured. So you have to figure out what the number of electrons transferred in this case is by looking at the overall reaction and the balanced half reactions. So once we have delta G and we have the temperature in Kelvin, we can make our plot. So if you look at the graph paper on page 287, that's what you're going to use to make your plot. But you're going to have to change the numbers on the x and y axes. So the x and y axes there have some crazy numbers, which I don't know where they come from. But here's my advice. When you're plotting, plot from minus 210 to minus 220 on the y-axis, and plot from 0 to 350 on the x-axis. That should capture all of your data. So that kind of helps you when you're constructing your graph to know what to make. So once you have your data points on, you're going to draw a best fit straight line through them. Now most of them are going to be in a straight line, except the highest data point may be a little bit off, so you're going to have to kind of account for the fact that that one's a little bit off. And that just comes from experimental error in real life. So your numbers are not going to be as perfect as my numbers are because you're going to have actual experimental data. So remember when you're drawing your best fit straight line to use a ruler, and you have to extend the line all the way to where it crosses the y-axis because we need to write off the y-intercept. Okay, so now we got to do some data analysis. So the first thing you're going to do is you're going to calculate the slope of the graph using two distant points of the best fit straight line. So we're not going to use our experimental data points. So we're not going to take the actual physical data points that I gave you. You're going to draw your best fit straight line with a ruler, and then over here and somewhere far over here, you're going to take two convenient points and use those. And the reason why we use the best fit straight line is because this accounts for all of the error that are in the individual data points. We're basically saying this is the overall trend through these data points, which have a little bit of variation. So you're going to read off the y values and the x values for these 2 points. This should be x2 minus x1. Sorry about that. I'll fix that on the custom data sheet. So you're going to take the y value and the y value and subtract them, and the x value and the x value and subtract them to get the slope. And then from the slope, you're going to calculate delta S. Now, if you remember, in delta G is equal to delta H minus T delta S, the slope is really minus delta S. So we have to take the negative of the slope because in delta H minus T delta S, instead of there being a plus, there's a minus sign. So we have to account for that by taking the negative of the slope. Okay, and then the next thing we're going to do is from the graph, we're going to determine delta G naught. And remember, this is delta G at 298 Kelvin. So you're going to find on your graph 298 Kelvin. You can draw a straight line up to where it intersects the graph, and you're going to draw a horizontal line over and read off on the Gibbs free energy axis what the value is at 298 Kelvin. And then that's going to be delta G naught. Then you're also going to get the value of the y-intercept and determine from this the value of delta H. So down here where this thing crosses is going to be your value of delta H. And you're going to write that down. Now remember what the units are here, guys. All of these units are based off of this axis, which are going to be in kilojoules per mole. So just keep that in mind. So then there are a couple of more points that you have to think about for the data analysis. It asks you, is the cell reaction exothermic or endothermic? So you'll have to think about what parameter you figured out in the last couple of lines will tell you this, and how you're going to figure that out. Then it says calculate the E cell at 298 Kelvin using the value of delta G naught. So over here we calculated delta G naught. We're going to use our equations, and you can look to see which equation allows you to go from E cell to delta G naught, and you're going to take that value that we got from the graph and then calculate the E cell at that for that delta G. Then also you're going to use this delta G naught or E cell to calculate the equilibrium constant for this reaction at 298 Kelvin. So you have to look at that chart of equations to see which equation will allow you to go between either delta G and KEQ or E naught and KEQ. And then the last thing you're going to do is you're going to calculate the standard reduction potential, E naught, for the zinc 2 plus half cell. So we give you the reduction potential for the copper 2 plus copper half cell, and you've determined the E cell from line 13. So if you know the half cell potential for the cathode and you know the cell potential, you should be able to calculate a value of E naught for the anode using those numbers and a proper equation. So this is the data analysis for this experiment. You can see that this was a nice simple experiment. You get a lot of very robust data from this experiment. It gives you very good values for delta G, delta H, and delta S. And this is a good way to practice a lot of those equations that you're going to be using in lecture to solve different types of problems. So if you have any questions, please feel free to contact your lab instructors, and just make sure that you submit the custom data sheet on Blackboard at the end of your regularly scheduled lab for this experiment. Okay, everyone, good luck.